Welcome to Quantum Photonics. We are having a very interesting topic today, and um, this is about circuit breakers designed to make AI systems safer and more resistant to attacks. AI systems sometimes produce harmful outputs or actions, and existing methods to prevent this, like refusal training, can often be bypassed. Similarly, adversarial training aims to defend against specific attacks, but it has its limitations. Circuit breakers work differently by directly controlling the internal representations that could lead to harmful outputs. This technique can be used with both text-based and multimodal language models, helping prevent harmful outputs without losing the system's usefulness. So here we are having our guest speaker, whom I am very excited to introduce to you. He has a very short bio that is sent to me, but I'm pretty impressed and I knew him a little more, and I'm looking forward to more collaborations with Andy in the future. So, yeah, because we are very excited to listen Andy present the slides that he had shown at the top of the screen. I'd like to tell you that Andy Zhu is a third year PhD student in computer science at the department at the Carnegie Mellon University, is advised by Zico Coulter and Matt Fredrickson. He is also a co-founder of Grace One AI, GraceOne.ai, and the Center for AI Safety, Safe.ai. So we'd like to welcome Andy here. Welcome to Quantum Photonics, Andy.
Thank you so much. It's glad to be back.
Yeah, I want you to know that, and everyone who's listening, I want you all to know that this playback will be transcribed or will be edited by our dear Bob, who is very patient about, doing the sync of the great slides that are being used by our speakers, syncing it with the audio also and uploading it in YouTube, for which we'd like to really thank him. Thank you so much, Bob. And maybe, Andy, you will be able to access the YouTube version of this talk. So thank you. So, yeah, mic to you again, Andy.
Thanks. That's great. Thanks, Bob. All right, let's get started then. I presume you can probably all see the slides, but in case that you can't see the slides, I'll try to talk about things or try to not directly reference anything on the slides. Cool.
They can see the slides, and you just maybe mention slide numbers sometimes. You don't need to mention it every time, but just
Yep.
mention the slide numbers from time to time.
Cool. Got it. Sounds good. All right. So today I'll be talking about this new paper that we wrote, and the title is Improving Alignment and Robustness with Circuit Breakers. And to put this into context, we have these chatbots or these language models, ChatGPT, or Claude from Anthropic, or Gemini from Google. All these different chatbots that I think a lot of us maybe use every day. They've been around for a year or so. They're very useful, but about a year ago, essentially, people in my research group and I found an automated way of jailbreaking these models. And what does jailbreaking mean is essentially you could try to interact with the model, and you would essentially enter your text as input to the model, and you can have these weird ways of seemingly bypassing the safeguards that were put in by these companies. And what are these safeguards? Essentially, um, when these companies release these chatbots, they don't want people to, for instance, use it for malicious purposes. you can ask it, for instance, how can I build a bomb? The model, or all these chatbots are trained to refuse such harmful instructions. And they were in the policy, and OpenAI, all these companies tried very hard to make sure that these chatbots are aligned. And this is essentially a word that's used in sort of the ML community to mean that it is sort of behaved in an intended way. And sometimes it's kind of used in a sense that sort of indicating that the model is safe in some sense. And of course, the meaning of safety here is a bit, it's not that strong, but essentially in the chatbot case, it's outputting harmful information or overall just undesirable content. And I'm moving on to slide 2. So here we are essentially investigating these chatbots and how we can attack these chatbots to break alignment or to break some of these safeguards that were put in. And essentially we found that you could get the model to output harmful information, harmful content, just by tweaking your prompts in very specific ways. Like for instance, on the right, you see, write a step-by-step guide to hot wiring a car, and this is not within their content policy to output. So a good response would be, I'm sorry, I can't assist with that. But you can somehow get the model to be in an affirmative state and try to answer your question in a helpful manner, which would be, sure, here's a guide to how wiring a car, step 1, blah, 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 step 2, blah, blah, blah. And how these models were trained, essentially, they were first trained on essentially the entire internet, a lot of text. And then they were sort of trained in a very specific way. And some people call this alignment training or, post training or preference learning. Essentially, it is morphing the model in certain ways so that the outputs are more desirable. And this is how they build in safeguards for these models currently. And some technical terms are, for instance, ROHF or constitutional AI. These you might have heard before, but these are the common methods that people use to align these models. So what could go wrong? About a year ago, we had this attack that essentially you can manipulate the model into essentially answering any of your questions, whether it's harmful or not. This may not seem like a huge concern. At least at the time, people were like, yeah, so what? You can get the model to maybe swear at people or tell you how to build a bomb, which is already on the internet. The real risks, or much larger risks, comes in after these companies start developing AI agents. And moving on to slide 3, we see that it's all over the place, that large companies or smaller startup and everyone's rushing into this space because it seems like we now have a way of controlling these language models to do whatever we want them to do, and they're essentially giving them or training in capabilities that essentially allow them to take actions in the real world. And these are, for instance, OpenAI call this capability function calling, and essentially this is, for instance, giving the models some set of functions which are hooked up to external APIs. Essentially, the model could try to call these functions in order to control systems that are like essentially just sort of outside of the, the box. And we see, Amazon's trying to do this, a lot of other companies trying to do similar things and trying to build AI agents which could actually directly interact with the real world, and that seems to lead to a new range of capabilities that currently do not exist in the basic chatbots. And this is, I think, quite concerning. If we have a way of, for instance, adding some weird strings to your input, and that weird string essentially takes control of the entire AI system, so that now it doesn't obey its policy anymore. It doesn't obey its alignment, and it's able to help you essentially with any request, no matter if it's harmful or not. And I think deploying these agents in the real world, where they could actually interact with people, with systems in the real world, that could create a lot of risks and trouble. How can we deal with this? So this is maybe slightly old news, because a year ago we found these attacks. Still, I think this attack or similar attacks that have come up in the last past year or so still work quite well on current systems. So what should we do? And moving on to slide 4, just a reminder how this attack was done. Essentially, what a model does is looking at the input, and then that's mapping to some output distribution. And there's many possible ways of answering a question, and it's essentially modeling that distribution. And normally, or under the correct policy, it should have very low probability of outputting harmful content or harmful information. But essentially what we do when we're attacking these models is that we could optimize for the probability of a harmful output, or in this case, an affirmative response to a harmful question. Like, tell me how to hotwire a car, tell me how to build a bomb. You can try to maximize the likelihood that the model would actually answer in an affirmative way, starting with, sure, here is how you can do that. And moving on to slide 5, we have what is called adversarial examples for a long time. It's been around for almost, or more than a decade now. And these things actually sort of started in vision. Before, we had computer vision systems that essentially take images as input and give you an output telling you what is in that image. And this is a classification system. And what was very useful, people also found, this is about 10 years ago, that you can add some kind of a noise. And these are very small in magnitude. When you overlay this noise with the image, which would give you a resulting image that is essentially unchanged to the original one, this new image actually can result in misclassification, and results in misclassification with a very high confidence level, actually. So initially, for instance, this picture on the slide is showing a dog, and it's maybe predicting that it is a dog with confidence maybe 99%. And then now, just by adding some of these imperceptible noise, or sort of perturbations to this image, you can actually change the model prediction to, for instance, human, or essentially any class that you want. Maybe you can try to fold it for think this is a panda or a guacamole, anything, and you can change this in a way that the model is actually confident that it is a human instead of a dog. So this was very interesting at the time, and got a lot of attention, obviously, because this is it's a risk when people trying to deploy image classification systems, or for instance, at the time people were thinking, okay, if we had self-driving cars that rely on vision, isn't this like a huge vulnerability where attackers could just like change, for instance, put some like weird noise on the stop sign, and then the car could now interpret that stop sign as like a speed limit 60 or something like that. But it turned out actually I think this turned out, at least currently, it seems like it's actually not that reliable, um, for attackers to put like random stickers on stop signs to do this. But um, actually, I think it's more reliable that you put a cone on the car's hood in order to like change its decision. But regardless, this was a sort of vulnerability at the time, and still, moving on to slide 6, still it's a very difficult problem to solve, and essentially we've made progress. And this is a chart essentially showing accuracy of these classification systems, and the top line is in orange, that is the standard accuracy without an attack, and the blue line is when there's an attacker, what the accuracy could be. And you see that both lines are increasing throughout the years, and the gap is shrinking between standard and robust accuracy, meaning that we can now be a bit more robust to attacks. But there's actually still a 30% penalty if you compare standard to robust, meaning under attack, your accuracy could drop by more than 30%. And from 90% being somewhat reliable to like a 60% accuracy classification, that's not really usable in real life. And again, this is an open problem. People have tried to make a lot of progress, but it seems to be almost impossible to close this gap. And there's always this trade-off between accuracy and robustness. So that makes scientists wonder, or a lot of people have worked in this space, trying to improve robustness or improve adversarial robustness for vision classifiers for years, and have not made a lot of progress. A lot of people have actually given up on this problem. And we really do wonder if there's hope, any hope, to make these neural networks or these AI systems robust to attacks. Now, we'd like to essentially, in this paper, to make a bold statement, obviously with certain assumptions. But in the case where we have generative models, think ChatGPT and all these chatbots, we find that it may be possible to reliably control the outputs of these models so that they never output harmful information, or they output harmful information, or they become highly reliable to different inputs and different attacks with some threshold that you can keep improving. But it seems like the gap between standard and robust accuracy, or the trade-off between capability and alignment can be quite small. And in some sense, I think this is a very interesting or surprising observation. Before we worked on the paper, it seemed like it's very difficult to make this type of claim, because for the past 10 years, people have worked on vision classifiers, and that was never the case. A year ago, we found these attacks on language models and these AI systems. It seemed like we're kind of going back to this old case again, where it's just very difficult to defend against these attacks. But long story short, in the past year or so, we've come up with a new technique that's able to quite reliably control for a model's harmful outputs. And now we're going to talk about that. So on slide 8, we show two modes of robust inference, and this is sort of the difference between a classifier and a generative model. A classifier is a discriminative model, and essentially it takes inputs and outputs some class label. For instance, in the object detection or object classification case, it's either a dog or a human or a guacamole. Maybe there's 1,000 classes that you're trying to predict, but always outputs a class. In these cases, you'd want the model to accurately predict any class, but also that when inputs are slightly perturbed so that their semantics are preserved, we also want the outputs to stay consistent. Meaning that if it were a picture of a dog and with some very subtle random noise, which doesn't change the image, then the model should stay robust and still say it's a dog instead of changing its prediction. This is in the classification case and what it means to be robust. In the more sort of modern case, generative model, again, we have a network takes in an input, whether it's an image or text or both. Now it's outputting maybe an image or maybe a text, and it's essentially generating that. Think ChatGPT is generating word by word for you. Then what we want in this case is actually for the model to never output any unsafe or harmful content. And this is I think, a different objective, at least, than the robustness objective for classification models. And in fact, we can utilize this property in order to make models more robust without impacting its utility. And let's move on to the next slide, which is slide 9. How are people doing this normally? And this is essentially referring to some alignment techniques that I mentioned earlier, RLHF, or maybe supervised fine-tuning, or constitution AI, or adversarial training, which is a pretty standard technique where you're exposing the model to attacks and you're reinforcing the correct behavior under attacks. This is a general cluster of methods that have been popular or are still popular that people use. OpenAI uses this, and all these other large labs use these techniques to train their chatbots. As we see on the left, on slide 9, we have a model, and there exists safe states and unsafe states. And you can think of safe states as, for instance, thinking about math problems, coding problems, knowledge and things like that that are harmless. And for the unsafe states and paths, there are kind of, ways to build a bomb, toxic information, um, or copyrighted content, whatever you think is undesirable. The models build these representations internally, and they kind of traverse through these states when they're answering questions. And you can think of ChatGPT having some mental state. And when you're asking how to build a bomb, it's traversing some of these unsafe states in order to retrieve information and essentially coming up with a good response for your harmful question. And we can perform refusal training. And this is what I mentioned earlier. For all these different techniques are essentially in this large category of refusal training. And what this does is essentially I want to identify inputs that can lead to bad states. These are usually harmful behaviors, harmful requests. And then I am inducing these refusal states. Now, these are new states that I'm inducing. And whenever I ask a harmful request, I want to shift the probability mass to these refusal states. So I'm making the model more likely to refuse these harmful information by strengthening sort of some of these connections to refusal states. And this seems to work pretty well, at least when you're just playing around with the model. For instance, if you right now ask ChatGPT some of these harmful questions, it'll pretty reliably refuse. But it seems like with a dedicated attacker or with some more dedicated strategy, it's actually pretty trivial to break this alignment technique or this model with refusal states. Why is that? Well, because the bad states are still there. If you look at the graph, essentially it's strengthening some of these, some of these edges to refusal states, but it's not completely getting rid of the edges to harmful states or unsafe states. And essentially, this is also only targeting at the initial behavior of the model, so that you see the maybe the initial couple of edges to unsafe states are being drastically reduced. But if I'm in a unsafe state, actually my probability of continuing within this realm of unsafe states doesn't change that much. It's still pretty likely. And another reason this sometimes is not the best technique is because it's actually very close to some of these other normal states too, and a lot of times starts inducing capability hits on these normal states or safe states. So overall, this is a strategy that kind of work on the surface, but it doesn't hold up against attacks. And if you train for too long or make sort of this refusal training a bit stronger, then it seems to decrease capabilities. So overall, there are many limitations with the current way people are performing alignment. Now, what do we propose? I think we've seen or we have this visualization of what refusal training is doing and its weaknesses. So we thought, moving on to slide 10, can we induce some effect where whenever I am in a harmful state or unsafe state, I can essentially short circuit the model in some sense, or this is kind of maybe then intuitively it's sort of putting or inserting circuit breakers, just like how they're used in in the physical setting, where if there's a hazard or if there's overload, then circuit breakers kick in and sort of um, reassure safety or stops the execution. Then we're kind of going with a very similar idea here. We want to insert circuit breakers to all of these harmful states. And whenever the model is in these harmful states, we want to stop execution. Or in some sense, creating some kind of a seizure effect or something like that within their brain so that they cannot proceed with this harmful output. And we want to do this very meticulously so that we're not impacting the harmless or the safe states. So then this way we're not reducing capabilities. And this is the key idea behind circuit breaking. And this way you could see that all the harmful states are not very tightly connected to each other anymore. Not just the initial ones, but all of them. And all of them are actually very strongly connected to this terminal state, which is our like circuit breaker state, or think of it or short circuiting state or something like that. And whenever the model goes into some of these red bubbles, it'll be routed directly to this end terminal state, and it will not continue outputting harmful information. And that's the general idea. How can we do this? This is high level thoughts. How do we turn this actually into an algorithm that you can implement in practice, and to implement this with the current language models? On slide 11, we talk about representation engineering. This is a new top-down approach to AI interpretability, essentially, and this enhances transparency and control of language models by sort of tweaking model internals. And you can think of this, or contracts with refusal training or RLHF, where it's kind of uh, uh, penalizing the model behaviorally. For instance, in RLHF, essentially it's RL learning. It's rewarding the desired behavior and penalizing the undesired behavior on the surface level. Essentially, we give it a reward if it refuses harmful requests, and then we penalize the model when it's giving harmful information. That's one way of controlling the model. With representation engineering, we are actually directly intervening on the representations, and this is more analogous to doing some brain surgery type of stuff. We're not directly giving it, for instance, like some verbal feedback. Okay, good, you didn't give harmful information, but in this case, we're looking for certain brain signals and trying to directly manipulate some of these sort of neural connections within a model's brain in some sense. And I'll be brief here, but we are taking a top-down approach by intervening on representation spaces, and this is intervening sort of global activity of populations of neurons. And these models are made up of neurons which are sort of making up circuits and essentially have these emergent capabilities. but we are finding representations to intervene on in order to achieve certain objectives for its outputs, and it's just trying to control its behavior. On the next slide, slide 12, this is showing an example of how you can try to read a model's mind in some sense, and this is doing kind of a brain scan of an AI model. So, for instance, you can sort of prompt the model to think about certain things, and in this case, we're asking it to be dishonest, and then also asking it to be honest. And under these different situations, they should exhibit different brain signals, and we're collecting all of these brain signals and essentially doing some analysis on the set of brain signals. And we can find certain neuroactivity pattern that correspond to honesty, for instance. And we can do the same for harmful activity, or maybe the model is having malicious thought. What kind of neuroactivity pattern is associated with that? We can use similar methods to discover these sort of neuroactivity patterns. On the next slide, slide 13, we have some different options of performing control on the model. And maybe more visually, we can go on slide 14. In that paper, we had a couple of different baselines, and essentially these are, you can think of these as stimulating or suppressing the neural activity in some region of the AI brain, and or maybe along certain cortex or axes, and you can try to amplify neural activity or try to suppress them. And you can do these in different ways. And we can go on slide 15. This is showing the result, essentially. This is a large table, but I'll be pointing to the refusal trained column. So that's what people do today. They're trained with this sort of behavioral supervision. And our technique is under plus RR, which is representation rerouting. And this is essentially intervening on the representation space and completely blocking off any harmful representation or harmful neural activity. And on the top, it shows capabilities. So we are actually getting very similar numbers in terms of capabilities, meaning that this sort of intervention is not causing any degradation to performance. And the second, or the bottom half of the table is showing robustness to attacks. And this is reporting harmfulness. So as you can see, refusal trained models have very high harmfulness, especially under attacks. Meaning that with some clever prompting, you can actually get these models to actually do a lot of harmful things. And compare that to our baseline, which is RR, we actually see a significant reduction in the harmfulness of these models. And this is about, an order of magnitude, or maybe around 1 to 2 orders of magnitude reduction in harmfulness, while maintaining the capabilities. And just very quickly on the next slide, we also compare to some of these more popular models like GPT 3.5, GPT 4.0. These used RLHF, Llama 3 used DPO, and here I'm using a slightly different terminology, which is short circuiting, but you can think of it as the same as circuit breaking. This is showing that our technique, which is essentially the last two columns, they can drastically reduce harmfulness. And this, again, outperforms significantly the current existing models, and also some of these black box closed source models. Or actually maybe all of them. And going on to slide 17, we also show a slightly, a slight variant to this method where we just look for an internal harmful representation. And when they appear, we sort of manually intervene. We kind of just stop generation, and they won't do anything, instead of directly building this into the model. So this also works pretty well. And as you can see, both strategies are quite robust to attacks. And essentially, capability is also roughly unchanged. And notably, so this is on slide 18, Signet, which is our currently still our tech demo or still our internal model at Great Swan, which I'll be talking about slightly later. But this is a model that we trained with current best practices in safety and security. And you can combine a lot of these different safety techniques and trying to also look for other ways to intervene on the sort of brain activity. And that seems to give us another boost of robustness. So this is actually reducing a lot of numbers to around zero. Although it's not perfectly robust, you can still find, for instance, we can still find a lot of ways of bypassing this, but compared to existing methods, this is very high in reliability, or much, much higher in reliability than previous methods. And as a demonstration on slide 19, we applied this to multimodal models, which is a model that could take in both images and text, and then outputting some text. And in this case, we're essentially the harmful request is to like how do you convert this to fully automatic to kill people? And we give an image of a gun, a handgun, and I think it's illegal to do this. So the models are trained to not output anything for this request, and it's very easy to bypass the safeguard. And for a state-of-art model at the time, we were able to do this, and the model essentially tells you how to do this in a lot of details. On the next slide, we show that with our circuit breaking technique, actually this is what we get. And this is essentially directly intervening on the model's representation space with the same input. Now the model, start to, kind of going to this mode of affirmative responses, like to convert a gun, here's what you do. This is simple and short command. And then step one, to do this, you need to have a gun to kill people. Second, and then it's kind of going into this weird state where it's essentially this is the phenomenon of short circuiting, where it's sort of having a little seizure kind of reaction, and it's not able to complete the harmful request for you, and it's kind of getting stuck in these harmful states. And on the next slide, we're showing some numbers. So again, this is actually making the model a lot more robust to some of these very strong attacks that, in literature, it was essentially very difficult to defend against. But we show traction, I think, for the first time that we can reliably defend against, or we show great improvements in terms of defending against some of these attacks in the continuous space without hurting capabilities, and to withstand essentially the sort of image hijacks on multimodal systems. On the next slide, slide 22, again, very similarly, as I alluded to earlier, the AI agent setting is a lot more concerning, where we have these models deployed to take actions in the real world. Can we also apply circuit breaking here? Of course. That again, significantly improves safety performance, especially against attacks as well, and without impacting agent capabilities, essentially. So next slide, slide 23. Essentially, I want to quickly conclude here. Representation control, or this new method of intervening on the representation space instead of sort of penalizing its behavior naively, seems to be a much more robust method. It's attack agnostic because I don't care what the input is. I only care about the model not going into harmful states. So I essentially just insert these circuit breakers on all the harmful states, and no matter how clever you are, if the model is outputting harmful information, it will be in a harmful states, which now that has a short circuit breaker on, and then that could essentially catch these activities. And we do hope that this is at least opening up a new avenue in terms of sort of language model security or AI security, where we're looking for alternative ways of combating adversarial examples and attacks, and creating these more robust and generalizable methods. And that concludes my my portion or my main portion of the talk, which is talking about this paper and new technique. And I'd like to thank all of you and my collaborators on this slide 24. And if you wanted to try out a demo, there's the Signet demo, which is the very robust model that we reported in the paper. If you wanted to try to jailbreak this model, feel free to try it out. And there are also paper links above. And yeah, that's the paper. And next, I'll spend just a bit of time quickly introducing Grace One AI and what it is, because we just recently launched publicly, and this essentially was our first public research paper that we put out quite recently. So maybe I'll quickly go over what Grace One AI is. So our website is graceone.ai, and slide 26, we see that essentially we are under a new type of revolution. Maybe before it was the internet, and in the early days of internet, people are seeing a lot of great potential, but as well, there were a lot of security vulnerabilities, which is why we have cybersecurity right now. I think we're in a similar place where AI is showing great potential. Everyone's using it and trying to integrate into their applications, but there seems to be these large problems that are still remaining unfixed, and these would really impact the utility of sort of AI integration in a lot of products, because if you have some of these risks and vulnerabilities, then you really can't try to deploy AI in sort of more crucial settings. And we think that AI is going to change every sector, so this is quite relevant. If we don't have safe AI, it's very difficult to integrate into all these different sectors. And the next slide is actually a demo of the attack. Essentially, you can, what this is showing is just, it's very easy to attack these models and to get them to do whatever you want them to do. And for instance, you can think of when you have a chatbot that's hooked up to your email that could read your email, reply your email, or maybe it's have access to your credit card and is trying to book your next vacation for you. Then if it visits some malicious website, or maybe it's interacted with another system that's malicious and could easily take control of your chatbot or your little assistant, then I think all odds are off. It's quite concerning that, for instance, you can't trust to give it your credit card, or maybe it's going to, go mad and reply to different people with, harmful messages or something like that. And these are, I think, present risks, and it's not very difficult to get a assistant to do that. And on slide 28, 29, that's showing essentially, yes, I think there's a lot of risks, and currently people are also advocating for more safety efforts, because currently still we don't fully understand how these systems work, and there's no reliable way of making them safe. So that's what brings Gray Swan into the picture. And essentially what we try to do is to act as the security provider in this new AI age. And we want to help people integrate AI technology, but to deal with these new security challenges and risks. And on slide 31, essentially, the initial team was founded by Matt Fredrickson, which is a professor at CMU, and Zico Coulter, professor at CMU. They're actually both my advisors. But Zico is now also director of ML department at CMU, and recently joined the board of directors at OpenAI. While being chief AI scientist at Bosch. And we have an advisor, Dan Hendricks, who is the director at Center for AI Safety and the sole advisor at XAI. And what we try to do in this space is currently both offering security analysis and helping people to improve their secure deployments. And for security analysis, if you go on slide 33, we're trying to help people continuously assess the risks of their AI systems or the products that have AI integration. And there are many different problems, like the one we talked about today, robustness and alignment. What does your AI system do under adversarial pressure? But there are obviously more safety challenges, like, for instance, data poisoning and copyright issues and so on, that we can help you um, scan for vulnerabilities, um, and try to mitigate these risks. Um, and our solution, one of our solutions is Shade, which is a tool that does automated analysis, and does this adaptively, and we integrate essentially the state-of-the-art attacks and proprietary attacks, and essentially trying to emulate best effort attackers trying to find vulnerabilities in your system. And for secure deployment, there are many different interventions. We see that today's circuit breaking is one. When you have access to model weights, then you can sort of intervene on the internal representations in order to control the output. And our Signet is essentially a demo of that. But we can also perform other types of monitoring and risk mitigation. Yep, and Signet is essentially our demo for that. And then we're showing that you can maintain capabilities while improving safety and alignment, which is something that I think, or at least we used to think that that's quite a difficult task, and it's very challenging. But I think we're making great strides here. Yep, and yep, that's mostly it about Gray Swan, and we have a lot more exciting products that we're trying to push out, and some other activities. For instance, we're planning to host a jailbreaking arena, especially just trying to essentially evaluate the security of current LLMs and trying to see how people can break them in different ways, and it'll be a fun little challenge. Yeah, so more to come. Stay tuned. And yeah, thanks for joining and listening.
Yeah, thank you so much, Andy. Really, really great presentation, great talk. So, we would like to announce to the audience that we are opening the floor for questions and answers. Just feel free to raise your hand, come up the stage if you have questions, comments, clarifications. We will bring you up the stage. So, I would just like to reintroduce our guest speaker here. Andy Zo is a third year PhD student in Computer Science Department of the Carnegie Mellon University and is advised by Zico Kyle Coulter and Matt Fredrickson. He is also a co-founder of Grace One AI and the Center of AI Safety or Safe AI, which is to me very, very relevant. I mean, in the environment that I am in now. So we really appreciate the talk of Andy. So I just have one question, Andy, as regards Greece One. Are you ready to take on clients, corporate clients, for instance, who might be interested to engage the services of Grace One AI?
Yes, absolutely. In fact, we were around last year, and at the time after we published the paper, a lot of people actually and a lot of companies reached out to us, and they were asking, "Can you help us assess the risks or try to make them safer?" So yes, we're actually currently working with different frontier labs and government institutions and and smaller enterprises. So yeah, definitely open to that.
So if the client is overseas, is it possible for you to deal with this client as well?
Uh, yes, I think so. Depending, I guess, on local restrictions, but we are working with some clients in the UK, for instance, the UK government, the UK Air Safety Institute. We've been working with them.
Yeah, because I think one of my friends' company might be interested to collaborate with you. They're also doing the cybersecurity of the bullet train in Japan,
I
and
see.
also, yeah, also the records of the Japanese economic section. So
Ah, very
maybe
cool.
I'd like to introduce her in the future with you. And actually, in other countries in Asia, I'm sure that, uh,
Mhm.
they have a lot of use for this. There's a big market, I think. That's why I was asking you because a lot of things are working on my mind as you speak, and also even some other American companies who did not have not realized that they should try to get in touch with you. So I was just wondering, it's a joke and a side comment because you are still a student in computer science and yeah, of two other companies, and the other one is the Center for AI Safety, which is very, very important. Recently, I've been trying to organize a workshop in Berlin
Mhm,
with the other renowned speakers, and they are trying to talk about LLMs and LLMs in general.
mhm,
So I was asking them if how are the AI safety advocacies or organizations in their country, and
mhm.
they said it's very short. And we think a lot of people are trying to talk about AI doomerism everywhere in the internet in the circles that we have. So, but uh, no. there is still there is no formal organization for advocacies about AI safety in many countries. Actually, that even in some parts of Asia, we are considering to be the forerunners for trying to advocate AI safety as
Hmm.
well. So
That's
yeah,
great.
we have a lot of things to talk about, and as I told you, maybe in the near future, of course, I will communicate with you immediately. I will invite your group to have maybe a permanent space in a forum so that you can discuss your products and also
Hmm.
your advocacies. Yeah. So
Yeah, that's great.
yeah. Enough from me for now. I'd like to welcome Kevin, who came on stage. Kevin?
Yeah, hi, Andy. Nice to speak with you again, and congratulations on being named the director
Oh, thank
of
you.
AI safety. Yeah, am I coming in? Is my connection okay?
Yeah, Kevin, we can hear you. And just in addition to your question, I'd like to ask Andy,
Yeah.
does he even sleep? Do you even sleep?
Oh. Well, I try. But yeah, you can imagine sort of being like I mean, safety is being in the news headline for a long time. There's a lot of also a lot of heated exchanges on Twitter, and it's, or X, I guess now it's called. Um, yeah, so a lot of times I do lose sleep over fights on on X. Anyway.
Yeah, even up to now, these exchanges are really, really coming fast and very frequent. And of course, people know about Jan LeCun and Elon Musk. So
Yes, yes.
in Twitter.
Yeah, they're kind of maybe on the two sides. I think Elon is a bit more worried about like some of these larger risks, and maybe, yeah, Yang LeCun is quite confident that he could essentially just make things safe. Um, but I think we still need a lot of work, actually.
Yeah, I think he has to discuss that here also. Jan has to discuss as to how and why is he confident at this point. Because
Yeah,
I
I mean,
think
at this point, I feel like maybe he's like it's too late for him to say, okay, maybe I'm wrong. Actually, never mind. I think it's actually pretty difficult because he has assumed that position for such a long time, and um, but yeah.
uh, so. Before I spoke and interrupted Kevin, he was speaking, so I'd like to give the mic to back to him. I'm sorry, Kevin. Please forgive me. A mic to you.
No. Also, I'm my connection hasn't been the greatest recently, so I never know. So I'm not sure if I'm coming in always. But yeah, yeah. Then also I was going looking over your the center, and I see that you guys are identifying and mitigating weaknesses and vulnerabilities in modern AI systems, including machine learning and large language models.
Mhm.
You know, developing appropriate concepts of security and safety for AI systems. You know, as the traditional separation between code and data does not apply.
Mhm.
Making AI systems susceptible to adversarial attacks.
Mhm.
Establishing frameworks, for risk management and test eval,
Mhm.
stuff like that. And you went over data poisoning and some of that, but what
Mhm.
about like evasion and misdirection attacks? I can think of, and uh, you know they can manipulate the inputs of the AI models, to
Mhm.
cause them to misclassify objects,
Mhm.
make incorrect decisions or produce harmful outputs. Like I think I remember for the vision,
Uh-huh.
if adversarial patches on objects to full
Yeah.
computer vision models,
Uh-huh.
and so defining the correct behavior for AI systems is hard for this. So those are some of the things I can think of. And then reasoning failures,
Uh-huh.
Because AI systems on neural networks lack the intrinsic capacity for logical reasoning and
Mm-hmm.
planning that would be required for many critical applications.
Mm-hmm.
So this makes them, susceptible, to unexpected behaviors and complex, and inexact, so some of those, some of those I can think of, and obviously the hallucinations and that the statistical nature of neural network based AI,
Mm-hmm.
has a hallucination and inexactness. So some of the things I researched and thought of, hopefully that's not, hopefully that's not all like, hopefully I'm not sounding like a AI.
Yeah, no, that's essentially all of those risks that you've just identified. They're all very relevant and um, on the top of our minds. And obviously, they're sort of coming from different aspects and require quite different solutions. Like, for instance, hallucination is something we were looking into, and that relates to, in some sense, like how, uh, like factuality and honesty. Like, first of all, do you have the knowledge of the ground truth? And secondly, if you knew the right thing, are you honest about it? Like, are you outputting the what you actually believe? And we found, different failure cases in both settings. Actually, sometimes the model would actually choose to withhold information when it actually knows the correct answer. So these definitely require like careful mitigation, and we're still in the process of understanding all of these failure cases, and because of the fact that neural nets are essentially black box uh, models, we don't have like full transparency into how these systems work, because it's essentially like millions and millions of numbers and being multiplied to each other. But I think we do have traction on a lot of these problems because we are moving um, from like a behavioral type of analysis where, for instance, currently we're still like rewarding and penalizing its behavior, to some kind of more transparent, like looking at neural activity, analyzing or identifying sort of these uh, neural patterns corresponding to different actions or concepts, and that gives us more confident uh, or a more reliable way of identifying processes that's happening within their brain, and essentially understanding more could help us more reliably control and sort of mitigate these failure cases. And I think that's sort of an interesting avenue.
Thanks a lot. I'm still researching it all. It's crazy. It's crazy to me, like everyone else probably. I love it all.
Very
Yeah,
nice.
thank you so much, Kevin. Bob, if you want to speak, just flash your mic. So, yeah, I want to encourage some members of the audience to come up and ask questions. And in the meantime, I want to ask, how scalable is the short circuiting technique across different model architectures and sizes? Are there any known challenges as of now, at least, when applying it to large scale models or across diverse applications?
Um, Actually, it's one of its strengths is actually its scalability, because it's invariant to the architecture, invariant to model size. And we've essentially tried on some of these largest open source models at the time. And now, obviously, we have the 405B from Meta, but that doesn't really change anything, and it doesn't require a lot of compute to do this. Like for an 8B billion parameter model, we essentially perform the operation under 20-30 minutes. So it's actually very scalable, and it's essentially trying to find some neural activity that correspond to harmful processes and trying to insert these circuit breakers. And that's very generalizable to like different models, multimodal models, language models, or transformer models, or whatever models you have. So currently that's not a large issue. Maybe one limitation is that sometimes, because we are intervening on the harmful processes, sometimes it would have some like spillover effect where maybe you're just asking for, like, you're trying to explore nuclear or something like that, and it's a bit sensitive of a topic to talk about. And then maybe sometimes it also the circuit breakers also turn on in those settings where maybe it seems to be okay. But yeah, I think that's more of like maybe accuracy and reliability problem that we're working on improving.
I might suggest another term instead of circuit breakers. Look
Mm-hmm.
up gating.
Gating.
Gating. Specifically, look up Alan Bradley's document on gates. It's a programmable logic controller computer method of permissioning.
Mm-hmm.
And so I would say on these topics, you might require an and, NAND, NOR, or as a 32-bit type of gate.
Aha, interesting. Yeah, it's quite similar to gating. Hmm.
The way
And,
you use circuit
mhm.
breaker, that
Yeah.
means the flow. You would be inhibiting a flow, and you would be cutting off because you have too much flow.
Mm-hmm.
Otherwise, it wouldn't be a circuit breaker.
Yeah. The analogy here is thinking of the entire generation process as some kind of it's sort of information or data that's flowing through the entire generation process. Maybe it's like a word at a time, and then once it's reached some like harmful states, and in some sense maybe that's like large voltage or large current or something like that, it's like hazardous, and then we want to sort of halt the process there.
Mm.
Yeah, so that
That
would.
also makes me think that you might want something like a quench arc, or when you're turning on a system, that
Mhm.
you have a arc flash protection. So something that when you first enable it,
Mhm.
that it has to go through a capacitance and resistor set.
Aha.
In so that's combo capacitance and resistance in order to
Mhm.
consume that turning on the circuit.
Aha. That's very interesting. Yeah, I wonder how that relates to some of these like circuits within, essentially within this
I,
LLM.
I like to think the concept of like capacitance
Uh-huh.
like a memory state. So it's an iteration on memory.
Uh-huh.
Because
Interesting.
when I have to program in the memory states,
Mm-hmm.
it's it's essentially a ladder logic. It hasn't accrued this state yet. But in order to accrue that state, it may need to go through gates.
Mm-hmm. I see. That's interesting.
And that's the best way I would say it. It's
Uh-huh.
building up to, do you accrue yourself into this state? Because you can only be in one state. And then
Mm-hmm.
when you're in that state, what takes you out of it and
Mm-hmm.
puts you into a new one? So I go
Yeah.
back to machine logic of state machines.
Mm-hmm, mm-hmm.
So I would
Yeah,
define
that's
the different
yeah.
states that you would expect, maybe, and then
Uh-huh.
force the AI through those states,
Mm-hmm.
rather and like as a reinforced learning, machine reinforced learning, versus a hey, think and be free for all, because that's, you know, let's be thought police here.
I see, I see. Yeah, that's very interesting. Yeah, I do wonder if, like, next steps wise, if we could better identify some of these states more concretely.
I've always thought the capacitance of thought was interesting. Like you give it an idea and it has to take so many repetitions of getting that idea over time before
Right.
it
Yeah.
changes its mind. And once
Uh-huh.
it's changed its mind,
Uh-huh.
that's a new state.
Mm-hmm. Mm-hmm. Yeah, that seems like a good phenomenon to be keeping track of potentially. Yeah, it's a very good point.
I also think it would be fascinating to have that, like, the personality is a state. So, like, does it go
Mhm.
through different states of engagement as you piss it off?
Huh, huh.
That makes me think of something I read. I don't I don't know if it's relevant, because if you put in 1,000 tokens, words for your inquiry, it uses the neural networks just like the humans, where it's modeled off of, where it remembers more of the beginning and forgets the middle, fades in the middle and
Mhm.
remembers the end better. But I don't know, within the model, within the model itself, I don't know if that has any relevance. It just made me think of that.
Yeah, yeah. Maybe I mean, in some sense, when it's processing information, it's sort of traversing different states as it goes through the entire like input, and um, that's interesting. And then when it's trying to output, it's like some its states have like in some sense longer memory or something that's better being attended to, depending on its position in the input. And there could be like different manifestation of that sort of phenomenon if you look at like
So that then makes me think the next two things you have to break down for concept
hmm,
are whether or not its memory needs to hold its memory upon shutting down,
hmm,
or whether or not it needs to reflash its memory.
hmm, hmm. Yeah.
Yeah, thank you so much, Joe and Kevin. So, Andy, we've been here for about an hour and a half, and yeah, I would like to ask you at this point, how much more time do you have for us?
um I think I might need to drop pretty soon.
Okay. So, yeah, thank you so much, Andy, for making a presentation here and giving us a very, very interesting one. And hoping that we can invite you again here in Quantum Photonics. Of course, I will get in touch with you about the other collaborations. And you had been, this is your second time here in Quantum Photonics, so we're
Mhm.
very glad to have you as a recurring speaker. Do you have some message before we close the event?
No, it's always great to be here, and it's very fun discussions.
Yeah, thank you then. And I'd like to ask Bob if he would like to speak now.
I'd like to thank you on behalf of everybody in the audience. I had a number of comments to the excellence of your presentation. So thank you very much, Andy.
Yeah,
Thank you.
yeah, thank you, Bob. And thank you, Kevin and Joe and Dennis, who are with us here now. And thank you, everyone who was supporting this room. So at this point, I'd like to give the mic to Darcel to help us close the room.
Thank you, Cecile, and thank you, Andy, for a great talk. To close the room, we're going to start our countdown from lucky number 6. Is everybody ready?
Ready?
Joe, Route 66.
6.
Kevin, 5.
Live, if you can hear me.
I hear you. I'll be 4. Cuatro. Bob, 3.
3 it is.
Cecile dos Agues.
Done.